Today we are designing a universal ammeter for ±100 amps. Besides, we are sharing interesting experience with AI. Some classic cars are equipped with an ammeter. We are developing a replacement that can be adapted to any style. As promised, here's an interesting experience with AI, bringing us back down to earth. Images creation is an impressive feature. You can define style, color, level of detail, background, and much more. However, even when trying hard, I can't manage to generate a usable dial. It's writing meaningless characters. No proper scale is generated, although that would be a pretty simple task. There seems to be no way other than using my modest natural intelligence for this. This example is demonstrating that the AI algorithm has simply no deeper understanding of what it is doing. Instead, it's just combining images corresponding to keywords. Back to the real ammeter. Is the battery currently being charged or discharged? And what is the amperage? Well, that was important in the past because car electrics were not as powerful as today. We are designing an ammeter using modern means, and you can use it to repair a vintage instrument or to create a new one in any arbitrary style. It could also be a cool gadget with practical value for your solar system. By the way, there are a few more videos on the subject here on the channel. Let's briefly talk about the working principle of an ammeter. With the classic method, you are measuring the voltage drop over a fed shunt, deriving the amperage applying Ohm's law. Microsoft Copilot seems to have a special relationship with shunts, by the way. It's painting lots of them into the image. The classic method has disadvantages, and for measuring high currents, I wouldn't recommend it to you anyway. There is a much better method using a so-called Hall sensor. Edwin Hall, an American physicist, discovered a voltage occurring on a conductor in the presence of a magnetic field. A Hall sensor is allowing us to measure amperage with galvanic isolation, which is a big advantage over the classic method. You can open it for easy installation. It's measuring direct, alternating, and pulse current. Don't confuse it with an inductive sensor, which can only measure alternating current. There are a number of versions available. I got the one rated for 100 amps, being able to measure up to 150. 1% accuracy and linearity are not bad for a reasonable priced part. 5 volts supply and 12 milliamps power consumption is suitable for our universal Arduino gauge module. And there is further interesting data. 5 microseconds response time is fast enough to measure currents, phase and spikes. Let's keep that in mind for later projects. Here are the sensor's connections for power supply, ground and output voltage. We will certainly investigate later what we can do with the reference voltage, but for the moment we are not using it. Up to 16 mm diameter should be sufficient, even for the massive starter cable in a car. This equation is giving us the output voltage as a function of the amperage, and even the flow direction can be derived. Here's the principle to apply the Hall sensor. For our Arduino code, we are rearranging the equation to compute the amperage from the measured voltage. At 0 amps, we are getting 2.5 volts output. At minus 100 amps it will be 1.875 volts, and I'm calculating some more values for the table. Using a lab power supply and a multimeter, I verified output voltages for plus and minus 10 amps. Let me draw the characteristic curve of the sensor, because it's explaining more than I could say in words. The rated plus minus 100 amps range is corresponding to a voltage swing of 1.25 volts. For the less accurate extended range, we are expecting a span of about 1.875 volts. How can we process the sensor's output voltage with an Arduino? The Arduino Nano has a 10-bit AD converter measuring 0 to 5 volts in 1024 steps. One step is corresponding to 4.9 millivolts. The rated range of 1.25 volts is relating to 255 steps, the entire range to 382 steps. Our stepper motor is moving 0.5 degrees per step. So 255 steps are 127.5 degrees pointer deflection. 382 steps are 191 degrees, sufficient for our planned amperage scales. A classic design could look like this. We were showing how to create it on this channel. This one fits a 1960s sports car design. I will show you briefly how you can create it yourself with a few guiding lines. Cool, isn't it? What do you think? Just comment me on that. In a minute I'm telling more about the Hall sensor. When manufacturing PCBs, we are relying on PCBWay, the sponsor of this video. Here's a PCB plus front and back panel for its casing. The parts came out perfectly. Great job. Kudos to the employees at PCBWay. Whether for hobby or professional work, you will find interesting offers on their websites. Take the easy way with PCBWay. Measuring electrical current using Hall sensors is an interesting option. Supply voltage, power consumption and output voltage are suitable for Arduino projects. Furthermore, galvanic isolation is a big advantage, not only for DIY projects. Applying a differential amplifier, you can compensate for temperature drift, etc., using both the white reference as well as the yellow voltage output. Feeding the reference voltage into a second analog Arduino input would be also an option to achieve that. Here's another interesting feature. The device presented has a potentiometer K for zero adjustment and a potentiometer L for changing the sensor gain. I will certainly test the ammeter in my car just to see modern car electrics at work. On a solar system, you could measure battery charging and discharging or power grid consumption. And especially with a self-designed dial phase, it would be a nice DIY gadget, right? Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.